Okay. So it's 6 o'clock. I'm planning to take quickly complete today's session, given that not a lot of questions are there generally these weeks. So yeah, let's get started, I guess. Welcome all to the live interaction sessions for the NPTEL ME97 course on applied numerical methods. The course instructor is Professor Malay Kumar Das, IIT Kanpur. I'm the teaching assistant, Shrey Sahai Gupta. I'm a doctoral student and at the Department of Mechanical Engineering, Indian Institute of Science. We have had six lectures, six sessions, not lectures, hands-on discussions and questions and answers uh, on applied numerical methods. Um, before I go, so what have we been doing? Essentially, the flow of the course has spread over 12 weeks. Every week is dedicated to a certain topic in applied numerical methods. At that point, we should give a disclaimer that the course is designed as a preliminary course um, to numerical methods. And so essentially, it tries to overview the big umbrella of numerical methods. We spend a lot of time in this course uh, on solving linear systems, basically AX equals to B. So essentially, the most canonical problem in linear algebra is AX equals to B. Uh, More correctly, it should be AX equals to B. Um, Bold. Or if I don't bold this, then at least this kind of, or let me bold this also. So this kind of situation is something that we have been looking at. There was a time when we appreciated the fact that this equation is ubiquitous. That is there. We saw that in our sessions on finite approximation methods. Essentially, what we do is reduce the entirety of our governing equations into this linear system of equations. So essentially, any linear system of equations can finally be represented as AX equals to B. So that is something that we uh, looked at. Now, um, um, what I would like to emphasize is that this was something that we were doing, uh, and now the course moves towards more advanced topics like um, uh, numerical differentiation, integration, solving ODEs, PDEs, and stuff. And while we can spend a small amount of time on those, the way these sessions has progressed, I see that we have been focusing on large chunks. Like we have focused a group of sessions on on a more fundamental topic like finite approximations method for around five lectures. I intend to again spend at least 2-3 lectures on um, numerical linear algebra, especially focusing on singular value decomposition. And the more I want to get into it, the more I realize that it is something that we can discuss um, uh, in more detail. So I this is one way of how I plan to so so this is why I actually plan to spend more time on this lecture, because essentially AX equals to B is ubiquitous. That is something that we saw in the very early lectures also. And there are other associated issues with it. So that is something that we should look at. Uh, and essentially, what numerical linear algebra is all about, if I have to sum it up, before I get into that, before I get started with this stuff, um, should I be revising other things? I guess not. Okay, let me get started. So basically, what are we looking at? We are looking at numerical linear algebra. And if I have to sum it up of what exactly are we essentially focus is numerical linear algebra what do we do in numerical linear algebra is something called as matrix decomposition, which is also sometimes called canonical forms, canonical representation, or matrix decomposition. And it is a good point in a course to actually appreciate what matrices are and what vectors are. So matrices can be given a geometrical picture, and it is very nice to geometry is very. I feel geometry is actually uh, a very important feature of a linear algebra. It is something that we cannot avoid. Like not assigning a geometrical picture to problems in linear algebra is a very uh, very I feel a very unwise proposition. It's not all mechanical. It is very theoretical. It is very physical, linear algebra, and it is important if we look at it. Um, some physical matrices, which I can think of, is and the way we should look at matrices is linear transformations. So. Uh, Before I get into that also, so actually, um, it is actually important to first appreciate what matrices are, and to before even go there, let's understand what tensors are. So tensors is something that one can look at, and tensors are actually a subset of matrices. We know these are square matrices, not necessarily they transform square matrices that that linearly operate over over vectors to result in new vectors in a different to a to a vector. And so essentially what I'm saying is that if we were to make up a rule, um, if we were to make up a rule, uh, say I want to map. So just like how functions are in real analysis, real number analysis, uh, we know for a fact that functions, what do functions do? They convert, they give for every x value, they map it to a y value. So what essentially a function is a function is essentially a mapping between x and y, so it maps x to y. But if we were to similarly map a vector to a new vector, um, then that can be done, and that can be done using a tensor, if at all this is a linear map. So actually, a linear map between two vector spaces is something that can say nicely define a tensor. So a more formal definition would be, yeah, a linear transformation that maps vectors to vectors, right? So between two vector spaces. Now, what vector spaces are is essentially a collection of vectors at the very least. And so the fact of the matter is, let's consider few tensors for say per se. So if I do that, um, let's look into a vector in R2. So there are. So first of all, let's appreciate what vectors are. Uh, And vectors can be very well defined in the Euclidean space, or even if you don't like that jargon, Euclidean, let's think in our physical space where we can define any point by three coordinates, x, y, and z. We know it's a three-dimensional space, right? So in a three-dimensional space, or for that matter, if we reduce our dimension to a two dimensions, that let's call it as uh, r square. This is the Euclidean space, two-dimensional Euclidean space. Essentially, this two or n defines the dimension of the space. Uh, so if we talk about two, in essentially, um, then we know that this vector, we know at least we know this kind of a vector. We know there is a vector called as unit unit tensor. There's a tensor called as unit tensor. What that does is tra a transformation, a linear map that transforms a vector to its own. So it does not do anything except so IU is just U. So this what that means is you are multiplying I with U to get another vector. In general, tensor is written in that sorts. A so SU gives me V. So this is what it is. Um, Note that tensor is a square. So tensors are ought to be uh, ought to be the way the tensors are defined. The v and u remain in the same dimension, so the vector's dimension is not changed as far as it this thing is concerned. And essentially, there are other tensors as well. So let's look at some other tensors. Um, some famous tensors. Uh, Let me think of it. So one very famous tensor kind of stuff is sigma is C epsilon. Uh, Just give me a yeah, where we know that stress and strain are two quantities, right? Stress is a tensor, strain is a tensor. Sorry, stress is a vector, strain is a vector. But when two vectors are to be related, or they have to be they have to be so when you want to say a vector is a function of a vector, then there comes the idea of a tensor, because a tensor is the operator which operates on a vector to give you a vector. That is the idea there. So let's consider when all in all what conditions do we have such situations where you need or when you have this requirement of representing a vector function, vector valued function as a function of space or vectors like that. One example is again, I remember we can have uh, u as a function of velocity as a function of x, right? We want to have a vector value. So suppose there's a flow field, right? There's a flow field, and in case of a flow field, you might have different velocities in different space, different points in space. Now, a point can essentially be represented by a vector between the origin and that point. So any point is a vector essentially. So this also a vector field is also when you have to write a vector field, you would require a tensor per se. So, for example, but it depends. So generally, if yeah, so let me think. Yes. So one example I remember is suppose you have a vorticity. Suppose you have a vorticity kind of situation. So you write there that V equals to omega. Then you have cross or times R, right? Where R is a vector, right? Omega is also a vector and speed is also a vector. Essentially, what that is doing is that you have a skew symmetric tensor uh, that you are talking about. And let me write that out, what that skew symmetric tensor represents. Uh, so how do you write the other function as a tensor notation? Essentially, you can do that. You can write it as a symmetric tensor so that you write it as WR. And actually, there's a very nice relation between W and capital, so that the tensor W and the vorticity vector omega. So W can be written as, let me write that down for you. Mm, How do you write that? Yeah, so W, Q, and R. Suppose this vorticity vector is, say omega is omega j cap or I cap or hat, I hat, let's say. Okay, so now actually you can write W as omega um, hat j. Then there is this operator called as dyadic product. Okay, let me show this operator. Where is it? Yes, k cap pqr. Uh, yeah, so it can be written as like this. Okay, uh, so this is j and this is k. Now, this is a new notation you might note, and this is very, it is more prevalent in linear algebra and graduate level study. But let me just quickly, for the sake of just completeness, let me give me the liberty to introduce these complex notations and stuff. Just trying to give you idea. Uh, Essentially, what are we doing is, let's say, what does this notation mean? So this notation means that if you this basically this represents a tensor, right? This represents a tensor, and if I want to write this, uh, u this tensor, this dyadic product. Let me write that dyadic product as, this represents a tensor. So u and v have to be two vectors, and the tensor characterized by this dyadic product will operate on an arbitrary tensor like this, which will be like v dot a u. Okay, so you see, it's the projection of the arbitrary vector along v. Uh, this is and the magnitude of that projection in the direction of u. So it becomes a little confusing, but I'll tell you how it looks like. What is this? Um, and what is this u? So suppose actually the correct way to see how to nicely introduce dyadic products. Mm, Okay, 1 second, give me a second. Okay, so the way to do this is, so are there famous tensors also? Let me also search some famous tensors to give you a feel. Famous one is stress and strain tensor, this stiffness tensor, I assume. What else? Examples, it looks like. Okay, there are no good examples. Let me just quickly see that about the dyadic product. Okay, is there a good picture? Okay, I'll show you what this dyadic product does. Uh, so okay, let me go back to this. I see that nobody has joined, right? Yeah. Am I recording or not? Recording. It's okay. Great. Okay. So what that is doing is, suppose you have this vector v. Let me give you a much simpler example. Let's say we are interested in this product. Okay, this one. Okay. What you will get is this, and essentially what you will get is, suppose this is A, and this is my uh, V, and this is my V. Okay, so let's say this is our A, right? And this is our U. Okay. So what this tensor is doing is it is converting this A into something of this sort. I'll choose a different kind of line to show this to you. Let me use this only. 1 sigma B. Can be a greenish line or something where this angle will be a 90-degree one. Okay, let me show this to you. So at least you know. Okay, now use this angle is 90-degree. Okay, let me write that down too. So what have I done? What have I done? Let me note that down. So this is the dyadic product. So let me Apurv is there. Let me talk to him. Is he there? Yes. Hi Apurv. You there? Are you able to hear me? Yeah, you have unmuted yourself. You can try to speak. Oh, he's trying to type, it seems. Probably he can't, he might not have a functional microphone. Anyways, okay. So let me, so I don't know if you can reply to me or not on the chat, or is that possible? I can hear him type, but I don't know. Okay, let's suppose he can't reach out. That's okay. Oh, he's audible now.
Yes, sir. Now can you hear me?
Yeah, I can hear you.
Yes, sir.
So, Abur, before, like, I was doing my own thing because we did not have any audience, but luckily you were there, fortunately. Do you have any questions for me before, like, I'd get into this stuff, or would you like to ask something, or do you have any something to discuss from like
Yes, yes, sir. If you could discuss shooting method.
shooting method that we can discuss actually. You want me to discuss shooting methods?
Yes, sir.
Uh, okay. Okay. So what is the problem that is being the problem that is taken in the course, the video lecture?
The Blasius equation.
Bloch's equation. Great. Okay. So I think just correct me of what the Bloch's equation is. Let I don't remember. Is it like this? Is it something of this sort? Let's check. Don't remember much. Let's check. Okay, so he's teaching Bloch's equation, huh?
Yes,
Good.
this is
Good.
this is the thing.
This is correct. Seems, huh? This seems correct. Great. Okay. And so what are the boundary conditions we have? Boundary conditions. One boundary condition is f of 0 is 0, and then the f dash of 0 is actually f dash of 0 is 0. It's not f of 0, we don't know, right? F of 0 is also 0. It's let me think. Oh, f of 0 is 0, right? Wait. Let me. So, has sir given the physical meaning? Has sir derived the Bloch's equation? So, f of 0 is 0. So, it's something like there is velocity u and then there is velocity v, right? V has a term of f, whereas f u is f dash of eta, or let's say eta, right? What is the notation sir has used? Can you tell me? Are you comfortable, Apur, to keep like chatting, interacting, or is it better
Yes,
if I
yes,
just keep?
no issue, no issue, no
No issues. Great. So V has a so U is the streamwise velocity, V is the transverse velocity, I suppose. What kind of is this the notation sir has used?
issue. Actually, he just directly started
Oh,
with this equation.
he tried to solve this, right?
Yes, sir. He didn't go much into the physical aspect.
Great. Do you want me to go into the physical aspect of it or
Ah,
just
yes,
try
sir,
to
yes, sir,
solve this?
yes, sir. I of- I think it comes from the Navier-Stokes equation, but like
It does. It
if
does.
it's
It does.
stream function, okay. Yes, sir.
So,
If you could discuss uh, briefly, that would be nice.
you want me to discuss that briefly or do you want me to discuss it in detail?
Okay, if you have, if time permits.
Okay. Okay, so just to keep it not very technical also, like not too detailed because this is not a course in boundary layer theory. Let's try to get the essence of Bloch's equation. Okay, so let's discuss what is the premise of the problem. Okay, this equation comes from the boundary layer theory. I don't know, sir, if sir has mentioned this part of it or not, but something of this kind of this is something that is expected. Okay. Now, what is going on? What is this line which I have tried to draw here? Let me clarify that as well. So what essentially we have is we have a flat plate. Okay. Mm, would you like me to give you a very nice detailed background also? Let me. Okay. So Apur, what happened in 1880s? No, sorry, not 1880s. In the 19th century. Yeah, in the 21st, right? Yeah, in the 19th century, basically 1800s, was the Euler equation available to us. Okay, you remember, you know about the Euler equation
Yes, sir.
or potential flows. You know about the potential flows at least. Let me also get that in picture. Okay, so I will not write any equations or stuff. Essentially, what we are doing is we have in fluid mechanics, we have three laws: conservation of mass, conservation of momentum, and then
Energy.
conservation of energy. Okay. Now, in 1800s, uh, people had what had people in fluid mechanics? People had cracked a few things. What they had cracked was, and they were looking at Eulerian Eulerian representation. Well, that does not matter too much here. What Eulerian representation mean is that we are kind of looking into fields rather than point Lagrangian approach. You
Control
kind
volume.
of, yeah, into control volumes. Great. So we are basically a control volume approach is sought, right? Okay. Now the backdrop of this whole Blochius equation was that people were what they did was that they were trying to, well, they had a airfoil. Let's say we have a airfoil, right? I'll tell you that suppose we have a airfoil. Let my airfoil be a ellipsoid. Definitely it is not a ellipsoid, but let it be an ellipsoid. Uh, Ellipsoid. No, not ellipsoid, ellipse. Let the wing be the cross section of the wing be a ellipse. It is not a ellipse, but just for the convenience of me not drawing a this thing, let it be a ellipse. Now, what it did was, suppose the problem is there is no heat transfer in the problem, and the flow is also low velocity. The flow is also incompressible, kind of speeds are low. The first thing that we'll notice is the conservation of energy will not give you anything. Essentially, what conservation of energy gives you, it tells you temperature. Is that correct? Roughly
Yes, sir.
speaking, loosely, roughly. Now, if it is known to me that the temperature variations are not large, and temperature is an imposition, you impose temperature, right? The temperature in this ellipse, and yeah, let me just one last thing, that there is a flow around this ellipse. We could have taken a ball or something, generally done in fluid mechanics and stuff. And this is the picture which we always see in fluid mechanics. The backdrop, I'm trying to tell you the backdrop of this whole Blashes equation, the introduction to boundary layer theory. Okay. So the fun thing is conservation of energy drops down because we say that the temperature is kind of constant, the temperature of the incoming flow and the ellipse or the wing or whatever aerofoil is the same. So temperature, there is no energy transfer happening, nothing of that sorts. There are there are details in energy equation, but let's say that those does not matter. Okay. Then essentially what we have is conservation of mass and conservation of momentum. Okay. Now, you might remember that there's a viscosity also pitches in. Okay. In potential flow theory, if you would remember, we say that suppose the flow is inviscid, then we kind of are able to write something of this sort, a Laplacian equation in stream function. If you would remember this, uh, by similar stuff. Let, let me write that. Or let me show it to you. Or why do am I writing this? Potential flows. Okay. So essentially what happens is when you say that the flow is inviscid, right? What the picture I was trying to show to you. That there is an aerofoil and there's a flow that is happening around it. And essentially we are saying, let's say the viscosity is also negligible, right? For air, we know the viscous effects are pretty much something that we do not, compared to honey or a more viscous fluid. We know that air is a very comparatively, relatively, or at least in a loose sense, not viscous. Let's say if that is our what do you say, ignorant assumption. Okay, then the equations that we will get is something of this sort. uh, the equation I was trying to write was there will be a whole lot of derivation, but at the end you will get something like this, something like this. Okay, and
Yes, sir.
they will even further reduce to that equation which I'm trying to. Where is that equation? Potential flow equation. Yeah, you kind of remember, but just
Laplacian
let me.
equation. Right.
Yeah, the Laplacian equation. Yeah, exactly that. Phi, double derivative of phi in x and double derivative of phi in y goes to zero,
Yes, sir.
equal to zero. Yes, not goes to zero, equal to zero. Now, what that did was it very accurately calculated the lift on this aerofoil. Okay, it did it so well, like it was. nearly perfect. Okay, and this 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 was calculated nearly perfectly. The lift, I'll call this force as lift L, denoted as so this was correct calculation. But if you remember again from the derivation, like from potential flow theory, potential flows says that there will be no drag, right?
Yes, sir, but yeah, because the flow is
If you,
inviscid, that is why.
that is inviscid, correct. The flow is inviscid, so there cannot be any drag, right? And it will not calculate it. So this theory will not be able to give you uh, drag. But now the anomaly was that if a theory is able to give you a correct lift calculation, why does the drag calculation fail? See, let's say you are sitting in a bus, right? What do you think is the majority drag coming from? Is it because of the skin friction drag, which is essentially like the flow that you're resisting at the surface? There is a friction or because of no slip condition, or is it because of also the pressure difference at the inlet of at the at the front of the bus, or some vehicle you're sitting at the front, or the first phase of the uh, obstacle, there is high pressure. At the behind there will be a low pressure. Because of that there will be a drag. What do you think is the major cause of drag? So is this is a pressure drag, a foam drag kind of stuff we call, or is it a skin friction drag? What do you think?
So if the front portion of the bus is very blunt, then it should be the pressure track should dominate, I think.
Right, but then that yeah, you're totally correct. But the problem is that this kind of stuff which I was trying to write, the Laplacian equation, is not able to give that. Okay, and part of you is, you correct. If you just include viscous forces there, it should give you, because Navier-Stokes equations are in very general. They are not much is left to like non-general, like generalize there. But still that equation was so 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 when you so basically uh what this is basically coming from, so this is potential flow equation. Okay, then conservation of mass is Navier-Stokes. Okay, and when you subtract Navier-Stokes, uh when you subtract viscous effects from Navier-Stokes, so Navier-Stokes
Give
minus viscous,
Euler's
viscous,
equation.
yeah, we get Euler equation, the Euler equation. The important thing to note is that Euler equation and the potential flow equation are identical. You can derive one from the another. Okay. Did you know that?
No, sir, I have not noticed that, but I'll try. It should be.
Yeah. Yeah. Because essentially it's the same thing. Potential flow
The
is the,
potential flow equation, this Laplacian equation, that comes from the conservation of mass, right? So,
yeah, they come from conservation of mass plus conservation of momentum. It has to be of both. When you couple them, you get one equation. You're right. So let me point that out too. So Euler equation, you're actually more correct. So Euler plus conservation of momentum, conservation of mass gives you potential flow equation, right? Or we call it as ideal flows. And this ideal word, so this is what the word was used. Ideal flow was used as a notation to mark that if we remove that viscous if we approximate the flow to be inviscid, we were able to very nicely calculate the lifts. But the problem arises, why are we not able to calculate the drags? Which you correctly said that we are ignoring the viscous effects. Now, one more important thing to note. very close to the wall, um, um, up to like it happened so that if you were to measure the velocity fields up to the very close of the wall, you would notice that it is uniform. So even around like if I were to calculate the velocity field by some measurement, we were actually noticing that the velocity was kind of slipping only. Unless we went too close, up to like a appreciable amount away from the wall, the velocity was very, what do you say? Like it was equal to the free stream velocity. So one thing which the experimentalists noticed was that it was not the viscous effect. Like it was not like the flow had originally become viscous. So I'll tell you what was going on. See, when we say that the flow is inviscid, so essentially, what are we saying? That this whole flow, this whole region is inviscid, right? Entire is inviscid, right?
Yes, and the fluid is slipping on the over the solid surface.
Yes. And now what these experimentalist people did was they tried to experimentally measure the velocity fields. Now, if there is a velocity gradient, because viscosity is related with, so shear stress is related with velocity gradient times the viscosity, right? So if there is a viscosity, there will be some velocity gradient. You remember that also, roughly?
Yes, yes.
So now what experimentalists saw was that there was no velocity gradient in this region. It was not there. And that was a big problem. They were not able to see any velocity gradients. At least let me be more correct to that. Obviously, there will be some velocity gradients. We are aware of boundary layer theory a priori, but essentially what was happening? Essentially, majority of the flow was inviscid. So if this is the region we are kind of, let's say this is the region that we are interested in, 99% of the flow was inviscid. 99% of the flow. Okay. And there was this existence of this thin region that we know boundary layer exists there, and there is where the viscosity exists and stuff like that. But essentially in the late like 19th century, people were not aware of this thin layer. At least they were aware that, yeah, velocity no slip condition has to be met at the wall, but they also argued that in the majority of the flow, it's true that the velocity will go to zero at the surface of the wall, but in the majority of the flow, velocity, there was no viscous effects. So they were not able to justify why viscous effects are that important. You get the idea, right? That majority of the flow is not viscous. So how come viscosity has such a important effect, especially on drag? Why is the drag not zero? And this is where Prandel's boundary layer theory came. What he did was he postulated that it is not that the flow is entirely inviscid. It is imperative, it is important for us to consider very close the regions very close to the wall, because it is where the effects of viscosity is so important that they kind of overpower, or uh, they are sufficiently high to affect the velocity, like, or the drag, or the skin friction forces. Okay. So that was the he postulated, it was his postulates. He postulated a existence of boundary layer. Okay. Now with that, so he had some postulates of boundary layer, that a thin layer exists. So he said that this boundary layer, let's say if its transverse thickness is delta, then he said that this boundary layer has to be very thin. He postulated that because experimentalists were seeing that in most of the flow, the velocity was actually the far stream velocity, or far stream velocity. So he said that delta has to be much smaller than some characteristic length of the geometry, which, let's say in the case of flat plate, is the length of the plate. So he said that this boundary layer is very small, very very thin, and then using this approximation and some very nice and very beautiful maths, he reduced the Navier-Stokes without removing viscous effects, but he did affect, like he did made some approximations. He was able to cancel few terms in the Navier-Stokes. He arrived at these, like there are boundary layer equations. So essentially boundary layer equations are Navier-Stokes after some boundary layer assumptions, which is essentially this and a couple more assumptions. I don't know, I don't remember if there are other assumptions also which have to be explicitly written down. Maybe a lot of things follow from this basic assumption, but essentially there are some boundary layer equations. Okay, now if you write that, okay, so now basically what you will have is you are trying to calculate the velocity field u, and you write something like this. Okay, and you write that u is u naught, where u naught is the free stream velocity. You write it as a function of eta. What is eta? Eta is this similarity variable. You must have heard the word similarity variable. Even if you haven't, it is essentially a scaled transverse coordinate, which is like y by delta. So depending on the local boundary layer thickness, eta is defined by this distance from the wall, scaled like some stretched thickness from the wall, kind of thing. Now with this representation, it is important to note that this f I'm using here and this f is also this f and this f is same. If I were to write a expression for v, just like how you said that du by dx plus dy by dy is 0, we can get an expression for v also. And if I do that, essentially what will happen is that we will have a term in f of eta. Let me correct this. This should be f dash of eta. So it's a slope. It's not f of eta, it's f dash of eta. Sorry for that. But if you see, so if I write partial u by partial x plus partial v by partial y is 0. You can note if I substitute this u as f dash of eta, note that eta is a function of y, right? And there will be a u naught also. You can actually appreciate from just from here that there will be an integration required if we were to find the expression for v. Do you agree?
Yes,
Right?
for we right. Yeah.
X, right? And if so, there is definitely a dependence of x on eta, but essentially what you see is that there is a f dash there, and if you do integration, you will get an expression in f v will be proportional to f. At least there will be a dependence on v p. Oh, okay, so what that does is we essentially, when we write everything, our boundary layer equations in this format, we will get this Blochius equations. I'm not doing that stuff here because this is not a boundary layer course. Essentially, this, what is this? This is conservation of mass plus conservation of momentum under the assumption of boundary layer that delta is much smaller than L, and writing U as this. Okay, this is called similarity transformation. It has a meaning to it. Why we are why see, U can be anything, but we are able to write it as this is a special approximation. It is a very nice, convenient approximation. It is a very powerful approximation. Let me point that out. But essentially, when we do all these steps, complicated steps, we get into this equation. And my point is that you know that at eta equals to 0 or at the wall, we know that um, the flow is also u is 0 and v is also 0. So u is 0. Uh, u is 0 and v is also 0, right?
Yes.
Now what will that do is the boundary conditions will be f of 0 is 0 and f dash of 0 is also 0. Now, can you tell me what? See, this is a equation in this is what is the order of this equation? Like, do you understand what an order of an equation is?
Yes, sir.
Differential equation.
Which one are you asking? So,
This
one thing I want to know, how are you defining f? I mean, sir defined it as a stream function.
okay. Uh, See, okay. Let me point that out as let us discuss that also. See, what is stream function? Phi psi. This is the symbol for stream function, right? Psi is, so you write u as e or partial
Dou y, dou psi by dou y.
dou y, right?
Yes, sir.
Dou y, isn't it?
Yes, sir.
And v is also equal to,
Minus would be that
yeah,
in any
minus
order.
dou psi by dou x, right? Isn't it?
Yes, sir.
Now you
Yes, sir.
see the way I have defined it is u by u naught is f of eta, f dash of eta, isn't it? Now you write this, go ahead and write this. Okay. So this will be 1 by u naught. Okay. So if you integrate now, so now let's say, because you know what is eta? Eta is, actually he was right to define it as stream function, but I'm just trying to point out it does not matter. It is essentially, f is. F is the profile of the velocity field near the wall. That is what it means. It does not have any. Definitely, stream function. It can be understood as, or we can understand it to represent stream function, but essentially stream function or velocity field or any other thing, essentially it is velocity profile only. So he's right, but stream function for me, that does not make too much sense as how as a velocity field, like velocity profile makes. So velocity profile seems to be more intuitive. So anyways, if we know that eta is y by delta x, delta is a function of x. Delta is only a function of x there. So in that case, if you do an integration, what you will note is, let's do an integration. Uh, this will be f of eta, right? And this has to be written as what? dy del psi by del y will have to be written as d eta by d, uh, yeah, d eta by dy,
dy.
which is what? Which is what? D eta by dy is 1 by del x. Isn't it?
Yes,
Just
sir.
check if just check if we do that, then this is there. Then you write it as delta of x, and this becomes phi. This is phi, I think. Psi of eta. Let's not write psi of eta or anything. Psi plus psi naught or something. Is is that correct? Did you get? Is that what you will get, right? Or have I made a mistake there? I will have to do it properly. I think this is fine. Do you want me to do it properly?
So
I
what
think
is
this is
the
okay.
so what is the third equation? So u by u not equal to f dash of eta, right? And that is equal to
Yeah,
1 by. 1 by u naught was I by
I
del.
just basically substituted u by del psi by del y. So if you do that, just remove del psi, just write del psi by del y. So 1 by u naught remains same, del psi by del y, right? Now I write this part. I write this part. I just go ahead, copy paste this, write it this, and then substitute this thing there, remove this. So now this is integrable, right? Because only f dash of eta is only a function of eta. All others are not functions of eta. So you will get this.
So yes, sir. So
You
we'll get psi as a function of eta, right?
psi as this. See, psi is this. This you can take as a proportionality constant,
Hmm.
and you see it's just proportional to f, just like how you said. Sir mentioned it as a stream function. And we know that psi naught at the wall, we can set the stream function to be 0. So you can actually go ahead and remove this. So you can just simply write f of eta is psi of eta divided by this thing. So this is the
Yes.
stream function.
Mhm.
Okay. Uh, okay. So let me go back to the fact that this is the equation that we will get. Now, based on the definition that we have used for f dash of eta, can you also tell me another boundary? See, this is the third order equation, right? Because the highest order of the differential equation is 3. And if this is a one variable, this f is only a function of eta, right?
Yes, sir.
So we will need three boundary condition, isn't it?
Yes.
So can you tell me another third boundary condition that sir might have used, or you can kind of tell me what is
So,
the third boundary condition?
so at y equal to delta, the shear stress will be zero. Can you use that?
Yeah, which is what? Shear stress is 0,
Yes, sir.
right? So we can kind of say that at y equals to delta, velocity is u naught.
Yes, sir. Some.
So f dash of uh, 1, you said delta, right? F dash of 1 will be what? Is
Yes, sir.
that correct? F dash of 1 is 1. Just look at this equation. Hold this.
Yes, sir. Yes, sir. It will be one.
Makes sense? Just
Yeah.
one important thing to note there is that this should not be f dash of 1. It should be f dash of infinity. Now you will get confused, isn't it? Why
Yeah.
not 1?
Yeah. Why not one? Infinity. It makes sense, but why not one? Yeah.
Why not 1 is because there is no sharp definition of boundary layer. You understand?
Yeah. Boundary layer is varying, right? Along x
Boundary,
direction.
yeah.
The
So
is varying along
essentially,
x
it is
direction.
kind of like exponential function. So I'll draw that to you like this. It's very similar to this thing. Stop hanging this time. Just don't hang. This mouse. Yeah. So it is something like this. Very analogous to the fact that if I were to plot e to the power minus x, where would you tell me to say that e to the power minus x is 0? Can you tell me a value of e to the power minus x where it is 0?
Yeah, minus infinity, right?
Infinity, not minus infinity.
Uh,
Why is it not? Yeah. So can you tell me a value, a finite value where it is 0?
it almost like near force. You can assume that.
Yeah. But did you see what you did there? You made an approximation, right? If we want the true solution, we will have to take the asymptotic limit. But if we want the inaccurate solution, a more inaccurate solution, we will, if we take f of 1 as 1, then what will happen is you will get a solution which strictly goes to 1 if it strictly goes to 0 at x equals to 4. But I'm saying that the solution of the boundary layer uh, is an asymptotic solution. Essentially, um, it, it is actually it is actually it will take some time for me to tell you why the solution of boundary layer equations is an asymptotic solution, why it is something like e to the power minus x and not something like um, I don't know, 1 minus x or something, or something like that, which goes to 0 at a definite point. It goes asymptotically, and it is kind of understandable if you try if you see that, because velocity will smoothly go to u infinity. It will never be u infinity, because do you get that why? Do you understand why it will be close to u infinity at very large values also, but it will not be exactly u infinity.
Yes, it is defined as 99% of the free stream velocity.
99%, right? But that is a weak definition. There is
Mm.
no mathematically 99% does not make sense. It is as arbitrary as 95 or 99.99. So that is
Mm.
why it's f infinity to get a true solution kind of thing. Okay. Now, now you asked me what are the shooting methods, isn't it? Um,
Yes,
now
sir.
you tell me you know how to solve a initial value problem. That is what you know, right? Shooting methods are coming in the context of ordinary differential equations, right?
Yes, sir.
And ordinary differential equations using methods like Runge-Kutta or simple Euler discretization or even more complicated, they are essentially solving initial value problems.
Yes, sir.
But look at the equations you have. This is not a initial value problem. This is not
Boundary.
even a boundary value problem. Not even a boundary value problem, because the other boundary is not even defined. But loosely speaking, we can do something to call it as a boundary value.
Why not?
Okay.
Why we cannot call it a boundary value problem? Because we have the boundaries, right? We have velocity at the plate that is zero. Then we
Other boundary is not defined, well defined. But you can, this is a construct I'm trying to make. You can call it a boundary value problem also. Not a, see, boundaries have to be well defined to call it a boundary value problem. This is again an asymptotic kind of stuff. It is going to infinity. But that
okay.
does not matter. That is irrelevant here.
The
If you
equation
draw
itself.
call it a hmm.
So the equation is third order, so we would need no. We have three conditions. Okay. Okay.
You
Yes,
can
sir.
call it a boundary value, no problem. Let's go ahead and call it a boundary value. But it is not an initial value problem. You need to note that.
Yes, sir. That is there. Hmm.
Right, right. Now the issue with boundary value problem is that you cannot proceed or you cannot evolve unless you have three equations in the um uh so the so let okay. Acha, tell me, Apurv, how do you solve this equation? Suppose I tell you f triple dash is, I tell you what f triple dash is. Let's say if I tell you f triple dash is this, let's make a model problem. You tell me what is, let's say it's half, 0.5. You tell me uh, what is the way you will solve it. Meanwhile, I'll open a nice book where this shooting method is nicely given. You tell me, how do you solve this? Any idea? With this RK4 or whatever you have.
But F double dash is there, right? And,
Actually, you need f double dash also. Hmm. F double dash you can calculate using the governing equation. You have f value, f triple dash value. Calculate f double dash at 0. You have it there. Did you get what I say? What I said? This, you have it, right? See, f of 0 is known, triple dash of 0 is also known. Put these values up here,
Yes, and
find
then
f
we get
double.
double dash.
Yeah. Now that you have f double dash also, what do you do?
Then we can use any method, right, sir?
Yeah, tell me how do you do it? I want to know which method you're comfortable with so that I can proceed in that direction, like in that way.
Let's say RK2.
RK2. So what is RK2? Can you tell me? Can you relate that to me? Just look at the notes or something, maybe online. Just tell me a method. What does the algorithm say? Well, what I'm trying to do is I'm trying to find a problem. This shooting method is given very well in one book as a problem. So I want to open that up and see before I do it with you. Mhm. Determine the blockchain. You're saying something?
No, sir.
Do you know how to solve the initial value problem as a whole? This one, or is that something that I discuss it first?
No, sir. You go on with that.
Just give me a second. The result of this operation is a formula. Let's read this together. Let's say if let's assume you understand this. Right, finite difference approximations and substitute the expression. The result of this approximation is a formula for calculus. Okay, then if equation is not reaction is repeated. F2. Nice. Okay. You tell me that I go ahead. Acha, tell me what topics sir has covered, like integration methods. Just tell me that at least.
Simpson's method or the one third,
Simpsons.
three
Simpsons.
trapezoid.
So integration. Okay. Let me open. Let me open that. Uh, Simpsons. Let me open Simpsons. But those are like integration. What do how do you solve ordinary differential equations? He must have taught you ordinary differential equations also, na?
RK2, RK2, RK4.
RK2. Let's do RK2. What is RK2? Lunga Kutta method. RK methods. What is RK2? Okay. Has he covered it properly? Like I know that he must have covered it properly, but do you understand it? What RK2 methods are for? Come on,
Yes,
man.
yes.
Okay, it's taking some time. What is RK4? I kind of remember it, but so as far as I remember, the problem, the reason I'm trying to explore it on the net is that I understand that RK methods can only be employed for first order systems. Is that a correct statement to make? How do you deal with a third order system?
Yes,
That is
that's
the
it.
that is the problem I'm trying to pose. I know how the solution also, but do you note
Yes, sir.
that RK4 Rungakutal? Wait, exit page. So keeps hanging every time I switch this one on. Wait. Yes, nice. So how do you first of all let's look at the problems like the definition thing. Um, Let me should I open the but the opening the book also will hang it. Can you search it on your thing and tell me what is the RK method says? Can you just read out the Wikipedia page?
So, as you pointed out, sir, we cannot use RK method in this one. It's higher order
Hmm.
ODE, right?
Hmm.
I think shooting methods are told that we convert, we take the boundary value problem and then convert them into a set of initial value problems, something like that. Then
Oh.
iteratively update the unknown initial condition to generate the known boundary condition, something.
So you're confusing. So you're confusing the shooting method. It's not the shooting method. The step one is not the shooting method. The second part, the guessing part, is the shooting method. Okay. What we do in this kind of situation is tell you what do we do.
Maybe we
See,
can take
essentially,
f double dash as g, so then f triple
right.
dash will be g dash, something like that.
Yes. What you do is you first of all realize that any order of equation can be written as a set of first order equations. Okay. So as you rightly pointed out, G, this one is hanging. Yeah. Okay. G is F dash. Then you write H is F dash, F double dash, and I is F triple dash. Okay. Then what do you write here is, uh, tell me how do you, can you help me out with this one? Now that we know, can you write three first order equations now? Essentially, what I'm saying is I want to write this, or let me do it this way, x equals to some function of x. Yeah, where x is a vector, something like this. So this is something that you will have to do multiple times at if you're doing solving ODEs. So this is something that you need to know. Okay. So let's say we will take F, G, H, and then also I. Okay. Then we will write f of x also. What is f of x? Let's write. So basically f of x is what? X dot. Is that okay? What is f dot? F dot is g, right?
Yes, sir.
F dot is g. What is g dot? I'm using dot, but you can use dash.
H,
What is h dot?
I.
And what is I dot? Use the governing equation here. So the highest derivative comes from the governing equation. So here we write it as f times h plus 2 times of I is equal. So not I. We don't need I actually. Wait, do we need I? H is actually we don't need I. Wait, we can do this thing here only. It's HF. What is H? H is F trip. H is see, this one can be written as 2 F double dash dash. Is that okay? Now you write 2 H dash or H dash equals to minus FH by 2. Is that okay? Sorry, FGF. Yeah, I think this is fine. Yes, yes. Is this okay?
Yes, sir.
If you don't agree or if you don't follow, just say I'm not sure. But do you agree or you're not sure?
No, sir. It's okay, sir.
It's okay. Okay,
Yes,
fine.
sir.
Then if it is okay, then you write it as FH by 2. Okay, that makes sense, right? This is f of x. Hmm? This is a non-linear this is a non-linear equation also. This is not a high third order linear equation. This is a non-linear equation also.
F is
Otherwise,
there.
what we could
F.
what otherwise what we could yeah, you're saying something.
Yes, sir. It's non-linear. Yes, sir.
Otherwise, if it would have been linear, we could have written something like this. Instead of writing f of x, we could have written it as a linear function of x. That is an important thing where A will be a matrix. Okay. Uh, and this A actually decides. Shivankit has a question, it seems. He's trying to raise his hand. You can type in the chat. I have some basic doubts. Tell me when I can ask. You can ask. Just give me 1 second. Okay. And then you can unmute yourself and ask. Um, so this A uh, decides how your system evolves. If it is a stable system, if it is a unstable system, something like that. And again, that will be a matrix property. So in a linear system can be represented by this A matrix. That is what I want to just point out. This I'm just mentioning that this as a motivation for the discussions I'm planning to have in the next subsequent sessions on numerical linear algebra, something that I had initially started. I was trying to discuss, but we'll do it later on. So you see, this A will have some eigenvalues. You must have already explored that in the course, and those eigenvalues are important. But we'll do all of that in subsequent sections. Let's now take Shivank's, sorry, not Shivank's question before we go ahead with the shooting method.
Hello.
Yes.
Yeah. Yeah. So actually, my question is like the initial value problem and boundary value problems are quite understandable. They are like quite explicit to understand. But what about the eigenvalue problems? Like, if you can explain what are eigenvalue problems and basically what physically eigenvalue shows there.
Before I answer that, I would need your help to tell me what an eigenvalue is. You can just Google it and tell me if an eigenvalue problem is in any ways corollary to uh, initial value problem or a boundary value problem. As far as I know, eigenvalue problems are not dynamic in nature. Let me search eigenvalue problems. What are eigenvalue problems? So what is the problem statement there? As far as I know, okay, this is the eigenvalue problem. No. There is another. So, Shivang, can you tell me what eigenvalue problem you are trying to refer to? Because there are a lot of
No, in general, like if we take
eigenvalue
no,
problems.
yeah, if we take any
Hmm.
problem like elasticity problem or anything, like so
Which problem?
basically
Which
what
problem?
like elasticity problems.
Okay. Hmm.
Yeah, so or like
Hmm.
a simple stress strain field problem we take, but it is of eigenvalue nature. Then what we do is like we try to find out the eigenvalues instead of going for boundary like boundary value. Like it is quite different from boundary value problem and initial value problems. So what I don't understand is like the physically what eigenvalues are showcasing to us.
That I will definitely discuss. One last thing which I want to ask is, are you referring to eigenvalue problems in the context of partial differential equations also? So let me show that to you what I'm trying to refer at.
No,
Or are you just
I
trying to?
think no. I think we can start from like if you can explain like what physically eigenvalues will represent, then you can move ahead with like what basically we target in eigenvalue problems. Because in boundary value we are very clear that we have to find values at boundaries. We need values at boundaries. In initial value
But Shivank, I
we
need
assume.
to. So
Yeah.
I understand your point. I'll definitely do that, no doubt. Just want to try to understand where did you get this term of eigenvalue problem? You said elasticity problem. What is the? Can you tell me the difference? What is the equation there we're trying to solve? Can you tell me that? Just trying to understand where are you coming from. I understand your question properly. I'll tell you what eigenvalues are. Don't worry. But I just wanted to get a feel of where you're coming from. Okay. Uh, would you like to answer?
Yeah, just hold on.
Yeah, take your time. No problem. So I have
The
a.
simplest, I guess the
Hmm.
simplest you can
Yes.
write is minus d by dx, a du by dx is equals to q.
Give me a second. Minus dy by dx.
No, minus d by dx, then y is a du by dx is equals to q.
So can you say it again?
A
dy
a
by
du by dx,
okay. A dy by dx. Okay.
a
Yeah.
small a. Yeah, yeah, it's okay. You can write it as you want. A
K. K.
du
You
by
meant K.
dx. K or whatever, it's just a constant anyway.
Can you take a screenshot and put it in the chat? It's a
No,
little difficult
it
to
was
hear
written
you.
in the, like, you are writing it right. Just write du by dx. Instead d by dx, you write just du by dx.
Okay, du by dx. This is this
No,
okay or
no. K is du by dx.
okay, du by dx. This one. Okay.
Yeah, equals to q.
Equals to
Q,
Q. Okay, great. Capital Q or small q. Does
anything.
not matter.
It
Anything.
doesn't
Okay.
matter.
Nice. Good question, Shivang. Okay. Let me point. Let's look at this one. Good question. It's a nice question because I'll tell you. Just give me a second. I wanted to show where this eigenvalue problem comes in. It actually comes in boundary value problems only. Uh, where is it? It's not here, huh? Must be, where will it be then? Let me try with Corpora. It will be in Corpora, I guess. Just give me a second. I just wanted to show, I
Yeah,
want to
yeah.
show this to you. Hmm. Corpora will be, where is Corpora? No. Hmm. It is somewhere. Maybe let me search diffusion equation. Diffusion or heat. Wait, I have it there. Let me open
Well,
these.
that equation also show like not only like elasticity, but it's also represent heat transfer also.
Agreed, agreed. So essentially, if I am correct, let's okay, because I'm taking some time here while trying to open that thing. Just one last time, I'll try to open this. Let me see if I have everything here. Unidirectional transport, polar coordinates, unidirectional transport, unidirectional transport. Let me try to show if we are trying to. No, this is not. Yeah, I think this is a eigenvalue problem. Let me check. This.
One more thing I want to add, like
Go
we
ahead.
generally calculate the eigenvalues of the system. So that's what I don't understand, like physically why, what does it interpret?
Actually, Shivang, it depends on the context very much. Okay.
Like if we say heat transfer in simple heat transfer equation, like say conduction, it is representing conduction only in that equation which I told you. So there, if I calculate eigenvalue, what is exactly it is interpreting? Like how we can say that these eigenvalues are representing something physical?
Got it. So when you say eigenvalues of the system, I have a different meaning to it because I am not a what do you say a solid mechanics guy. So I might not be able to answer you properly there. But I think I see. Think this is where eigenvalues are coming in. I'm trying to open a slide where eigenvalue. I've solved the
You
eigenvalue
can,
before. I'm just trying.
yeah,
Hmm.
you can go ahead with heat transfer. Don't worry to go for solid mechanics. We can go
That's
discuss
okay.
heat.
In vibration
Yeah.
also eigenvalue problems comes.
Yeah,
Vibration.
yeah,
Yeah.
yeah. That is
So
actually
yeah,
the there actually if we
I
can eigenvalue,
understand.
we can
See.
understand. We can understand eigenvalue very easily their vibration, but in heat
Yeah.
context of
See.
heat
This is
transfer
this
and
is where.
solid mechanics.
Okay. Okay, Shivang. Now I'll show you what I mean. Okay, good. I found this. What I was looking for. Okay. See, it was actually important for me to first write down the equations which differentiate a eigenvalue problem from an initial value problem to a boundary value problem. Let me first point out to you, as far as I understand, eigenvalues problems are when in context of initial value equations, they emerge from a boundary value problem only, first of all. Okay. uh, and they kind of appear generally in linear differential equations. Suppose this is my domain. Suppose this is a heat condition kind of thing, and I have given this is my domain, a rectangular geometry, and I have four temperature boundary conditions at each face. Okay, this will be my equation. You guys agree? This will be a simple del square t by del x square plus del square t by del y square equals to zero kind of situation. Okay.
Actually, this is the same equation which
Now,
I told, only Q is zero there.
no, there was also a y there. So you
No,
didn't
no,
mention
Q
del
is
square
zero
by.
and yeah, Q is zero and A is one in that equation.
I knew. I know. I got it. I knew that you were mentioning the same thing. Now I'll show you how eigenvalues pump in. Okay. I'll show that to you. So what you will see is you try to solve these things, and because the equation is linear, you do a separation of variables. See, you have two variables. See, it was important because you didn't mention y there. It is actually important to mention a second variable there. See, boundary value problem can be two-dimensional. It can be one-dimensional problem also. But in a two-dimensional kind of situation, if it is a linear equation, okay, separation of variable can be applied. Okay. I think yes, that's true. In a linear differential equation, you can apply a separation of variable technique. Okay. Now, when you do that, what you realize is that because of the this separation of variable condition, that a function is a multiplicative function of f of x and g of y, and then it has to exist that when you separate the two, like how we have done in this step, it has to be a constant. Now what that is doing is it's bringing this lambda square kind of stuff. Now why it is bringing lambda square, see, do you see this? Now you will also note that this I have taken it as a lambda square. I've taken it as a positive term. Okay, and not a negative term or anything. I have concluded that whatever constant this is a positive constant. Let's first try to understand this problem, then we'll come to the eigenvalue of part of it. Just follow what I'm trying to bring it here. Note that our solution has to be a finite solution. Is would that be an important requirement, right? That our solution has to be a finite solution. Now you realize that in this kind of situation, f double dash by f is a constant. What kind of solutions are you expecting? When is f double dash by f a constant? Shivank. Or G double dash of G is constant.
Actually, I'm
Yeah.
really
And
sorry, but I don't understand this thing. That where we started is actually we have
so
this
you
two
need to
conditions
follow. So
and
you need
one.
to.
No, just a minute. We have these two boundary conditions like TA and TB that's we have already, and two more conditions are there, T naught and these things. And
See, Shivang,
what?
I need to drive this. Wait, I need to drive this. So yeah, you can't discuss it on on mic. My simple question is, do you have any function in mind which follows that its derivative, double derivative is proportional to its original function? Like the simple answer is sine, sinusoidal or cosine functions. Now, did you get any idea of that? You know that, right? Sine, double derivative of sine is proportional to sine.
Yeah,
See, you don't
but
need
can
to
you explain
follow.
what? No, just a minute.
Yeah.
What we are doing? What, T star we have written it as f, a function of f, x, and gy. What is this? Can you explain it?
So yeah. Okay. So first of all, I was assuming that you were referring to a similar problem as you mentioned. So I think something of similar sorts was happening in your in your problem also. Is that not the case?
No, that is different thing.
That is a different thing. Okay, so let's settle on that. So we are talking about a different thing. Fine. Okay, but now let's discuss this part because I am not sure and I'm not sure of your what problem you are discussing. Let's discuss this problem. A lot of times, in this diffusion equation, as you mentioned, that at least you agree to this part that this equation is the equation you are trying to discuss as well. If you have this boundary condition, set of boundary conditions, and this rectangular domain, you have two independent variables. Do you agree? X and Y. We are talking in space coordinates. X and Y. Do you
Yeah.
agree?
Yes. Yes.
Okay. Now a function can be it's a function of two variables. Now, the proposition is that one way, I think you have taken some differential equation course in your curriculum. There is one method called as separation of variable, integration by separation of variable. Or even if you have not heard of it, we assume we move ahead into our integration, into our solving a problem by assuming that our original function t star or t of x comma y is multiplicative functions of uh, separate variables like f of x multiplied by g of y.
Okay, now understand. Yeah, yeah, yeah. Yes.
Okay, have you seen that before?
Yeah, I'm just guessing that you are assuming a solution which is a multiplicative solution, which is having a function of fx and gy. So it is making a sense that what you are trying to
That's,
find out is a
but you're
function
not.
where we are trying. Yeah, variables available, I know, but it is not in this way.
Now, if we substitute this aspect of it into our original equation of del square t by equals to 0, what we'll get is because g of y does not depend on x, so it can be taken out of the term del square by del x square. Similarly, f can be taken out of the operator del square by del y square. And so we'll get this kind of equation. Now, because this has to be 0, the following equation follows. Okay. Essentially, because this has to be a constant and the solution has to be a finite solution, what do we get is that f of x gets to have an exponential form. Either it will be e to the power lambda x and e to the power minus lambda x. Now, you get that, right?
No, no, just
Essentially,
wait a minute.
cosine or sine function.
Wait. Up to this
Okay.
point, it is clear that we have assumed a solution and do all these things stuff. Why we have assumed it lambda square? What is the attempt here?
So that I'll tell you, but the important point is that if this is not the eigenvalue problem you're referring to, I would like to understand the eigenvalue problem you are referring to. So go ahead and tell me that because this is something that will take like it will not take time, but again, it's stopping me to like it's coming in the way of me to explain it to you. I would also want to know what eigenvalue problem were you talking about? In what context?
No,
If
I'm
this
in
is not what
general,
you
I'm
were referring
no,
to.
in general, there are three types of
Go
problems,
ahead, go ahead,
eigenvalue,
go
boundary
ahead. Tell
value.
me the in general. Go ahead and tell me the in general eigenvalue problem you have heard. Like, where are you? Where have you heard this term? Just want to understand that,
I know
because
it's
this is not a typical eigenvalue problem. See, this can also be an eigenvalue problem. See, this can also be an eigenvalue problem.
I, the thing is like there are three types of problems. One is initial value, second is eigen boundary
That's not
value,
true.
and third
That's not
is
true.
eigenvalue.
That's not true.
So I
That's
am
not true,
yeah.
Shivang.
So
That's
what
not
is
true.
true?
That's not true. That's not true. That there are three kinds of problem. There are only two kinds of problem, loosely speaking. Initial value problem or boundary value problem. Eigenvalue problems are not in the same class as initial value or boundary value.
Can you
That is why
explain
I'm
me
trying
what
to
are
understand.
eigenvalue problem? I don't know. That's why I'm asking.
See, the problem is you're telling me that I have a question, but you're saying I don't understand the question also. I don't understand what I get. So that is why I'm trying to understand where you're coming. Like, where have you picked this word as eigenvalue problem? Only then we can discuss that, right? Because eigenvalue, see, this can also be an eigenvalue problem. Find the eigenvalues of A. This is also an eigenvalue problem. Are you trying to understand? Are you trying to ask me that? I can go ahead and tell you what eigenvalues are. So see, what eigenvalues are, see, a matrix can be always looked at, not matrix. Eigenvalues are only defined for tensors or square matrices. Now, what a matrix, a tensor do, or a square matrix do is, it is a linear map between two vectors. So if in your case, because stress is a vector, strain is a vector, right? So the stiffness matrix or stiffness tensor transforms, it actually relates stress and strain, right? You understand that, right? But if we look at it as a function, what is it doing is it is converting the strain tensor to the stress tensor. Do you agree? Sorry, strain vector to the stress vector,
Yes.
right? So essentially, eigenvalues are defined for tensors in general. Now, what a tensor does is it transforms it, it maps one vector, a vector space, or what it will do is it will operate on a vector and make it another vector. Just like how a stiffness tensor operates on this stress strain tensor and makes it a stress vector. I might be using the words incorrectly. Let me, yeah, but that's okay. So you understand a vector mapping it to another vector. Eigenvalues are associated with the eigenvectors also. Eigenvectors are directions or vector directions along which uh, a tensor does not affect the direction. So when you write AV equals to lambda B, essentially what you are saying is that these eigenvectors are special directions associated with this matrix or tensor, which does not, so upon operating on these vectors, they do not affect the direction. At least if it was in earlier in this direction, suppose some direction, some eigenvalue, the operated or the final vector will also remain in that direction, first of all. But what can happen is it can scale. Either it can scale up to let's say it can be scaled to 100, it can be shrinked, or it can be brought to 0. That is eigenvalue, the amount of scaling in the direction of eigenvectors. That is the geometrical picture or the physical picture that can be given to eigenvectors. That is uh, one picture that eigenvalues hold, or one explanation that eigenvalue holds. Eigenvalues can hold different values or different um, meanings in different contexts. Another context of eigenvalues come in the context of what I was referring to earlier. Eigenvalues sometimes, so what happens is it is actually kind of all related only. If suppose this x dot is dx by dt, okay, dx by dt, then the eigenvalues dictate that if your solution will grow or shrink or go to zero in time. Because how I mentioned, right, the vectors are operate like this tensor is operating on this vector, isn't it? So essentially, either it will be stretched or it will be shrinked. So that decides whether your value will increase, will it explode, or will it go down. And there comes the notion of stability. So there we say that if all the real parts of the eigenvalues are positive, then you have a stable, sorry, if they're always negative, then you have a stable system. If they're positive, then you have an unstable system. So eigenvalues in are, see, most generally eigenvalues are always associated with a tensor. And then depending on the application or the differential equation you're dealing with, their meaning changes, or you can construct a meaning around that as well. So that is the short answer I can give you right now. If you have any follow-up, you can go ahead. Or did you, if you not understood what I mentioned, then you can object.
Actually, the thing is, one thing is like that scaling thing is, we call them
Not,
simply scalar. Why we'll call it as eigenvalue? They are simply scalars, which scales that vector.
yeah, eigenvalues are scalars, aren't they?
Yeah, actually. Yes.
Eigenvalues are scalars. There are eigenvectors which are vectors. Eigenvalues are scalars. You are right.
Okay.
But
So
the important thing is, that a matrix will have a set of eigenvectors, right? In
dip,
that direction, how much scaling does that vector do? Defines that sorry,
I
a
understood your
matrix or
point.
a
Can you, yeah, just a
hmm,
minute. Can I put it in different way? Just tell me if I am wrong. So
hmm.
I can relate it like this. Like we have unit normal vectors, simple ijk, and we scale it using a scalar. Similar way, we have eigenvectors in a particular problem, and we scale it using eigen values. Can I make
No,
this similar?
that's not, no, no, that's not correct. That's not correct. First of all, you need to understand that whenever you are mentioning eigenvalues and eigenvectors, there has to be a associated tensor that you're talking about.
Okay.
That can be a tensor of your system associated with the system defining your system. Let's say there's a dynamical system. You're trying to see if a value in time grows or increases. Or in our case, like how we were trying to solve our initial value problem. If it were a linear system, I would have written that this vector x, either it will grow to infinity, its different components will grow to infinity, or all of them will go to zero, or it will go to some finite x, some x naught value. What will happen to it? But that is governed by what? Some tensor A. So in context of eigenvalues or eigenvectors, you have to talk about a tensor. Eigenvalues don't make sense without a tensor value. Now, what is a tensor? Tensor is essentially telling you how your system is evolving, or how does your system behaves in context of, say, solid mechanics. Stiffness tensor
No,
decides
no,
your
wait. You
stress
can
strain.
go. Please go by heat
See, you
transfer.
can't
It's fine.
interrupt me. See, Shivang, there is a little bit of courtesy. You can point, you can raise your hand, but let me complete, right? You can't just keep interrupting me. So yeah, but you interrupting me. Go ahead now. But next time, just avoid that. Yeah.
Okay, I am saying you can go by heat transfer. It's not necessary to go for stress
No,
strain.
why not? Why not? Why not solid? I can give an example, right?
Yeah,
How
but
does it
actually in
matter? How does it
heat
matter?
transfer, it is more visually, I can imagine. That's why I'm saying.
Okay. Okay. Fine. In a heat transfer problem, the thing becomes complex, because then I have to go to this kind of picture. And again, as I point out to you, if you have not seen this picture, it does not really make too much sense, or too much. It is not a good motivation to explain eigenvectors to you. Okay, so that's not a good idea here. So there is no heat transfer problem at hand for me to discuss. If you have some, you can go ahead and tell me. See,
Okay,
eigenvalues
then
and eigenvectors have to be complemented with some matrix or some tensor. You have to give me that. Then I can tell you what that gives you, what is the physical meaning associated with it. Only then I can do that.
okay, then you can take strain or stress vector.
Yeah. So as I was saying, there are, in stress or strain, you know that there are regions of, or directions of principal directions, right? There are directions along which the stress, the object or the material is just stretched, right? Or compressed. Principal directions, right? So in those directions, you see how the material is not changing, sorry, is not changing the directions. In other directions, either it will be it will be rotated and what do you call it? Um, Rotated and stretched, skewing, or whatever what is it called, shearing kind of stuffs will happen. But in those directions you will have only normal stresses, right? In the direction of strain, the stress and strain will be parallel, right? So in that picture you have this tensor and stiffness tensor. So always a tensor is operating on a vector, giving you another vector. There are special set of directions for every tensor. There are special set of directions along which it does not rotate the vector. It only stretches or compresses the vector. The amount by which it stretches or compresses the vector is called eigenvalue. The directions are called eigenvectors. That is the whole picture. That is the whole idea there.
Okay, so they are like principal directions where it's like, and I'm trying, like I understand, but your point, but are there such as directions where only they are stretched, and they can be stretched, and that can be done, like,
Yeah, why not?
okay.
Oh, let's discuss this. Let's see. We call it principal directions, I remember. Let me check. Not very.
Yeah, their shear stress is zero, so only like we have normal stresses, and that can only be stressed or something like that. So
There are, so I think this is done in um, what is that? Is it done in one Mises? What is that? Moore circle. Moore circle में होता है ना? I don't remember.
no,
There
in
are
actually,
directions, obviously.
yeah,
Hmm.
in shaft, if
Hmm.
you apply torque only, uh, then we
Hmm.
have such kind of element at the top where we have only
Yeah,
uh, shear stress, and
hearing compression or stretching going on. Yes.
yeah, so those are actually eigenvector directions, I can say, like, and that
Yes,
can
yes,
be,
yes, yes. Yeah, yeah, yeah. That is
wow,
the
that's
best way to
wonderful.
understand. Yes.
And that was a really nice explanation.
No,
Thank you.
that is the fundamental explanation. See, there is no other explanation to eigenvectors or eigenvalues. You
Yeah,
see, people when write this equation, this is the equation you must have looked every time, right?
yeah,
You must have looked at this equation always, right? What the physical picture is there, similar what I said, that a tensor has to be looked at as a map between two vectors. It is transforming, or it is operating. There's an operation going on a vector. It is somehow moving that vector in some direction, stretching, straining, shearing, or something. There are always, along for a tensor, there are always directions along which it does not affect the direction. Those are eigenvectors. The amount of scaling or compression or whatever, the amount of scaling that is happening in those direction are eigenvalues. That is the picture there. We
yeah.
can go ahead.
And
Now we can go ahead.
okay, so like depending upon that, I can relate it to like they are kind of a spatial direction in a particular set of problems. eigenvectors, where we
See, the
can only
problem
scale
with
and
associating it with directions is a problematic prospect. I'll tell you why. Because unless you have a matrix defined, see, I have not heard of any problem with having only eigenvalue. So, can you tell me an example of where you say that eigenvalue of a problem or eigenvalue of a system is so and so? There is nothing like that.
yeah,
Uh, There are there are eigenvalues of a system. I'll tell you in what context. But even there, you don't call them as eigenvalues of a system. You call it something else. Do we call it
yeah.
this eigenvalues of a problem? Let me think.
Can I say something?
Yeah,
One
yeah,
thing.
yeah. Go ahead.
Like in boundary value problem, if the boundary where this either u is equals to u naught, or like the place where tau is going to be zero, wall stresses are
Mhm.
maximum or something like this. So these are extremities of those problems, and these extremities can be represented in form of eigenvectors, because they can only be, they have a certain fixed kind of thing. So can we say that those things can be come under the category of eigenvectors? Like, I just want to have a physical interpretation. That's why I'm asking, because anything,
Interpretation. See, if you're going for an physical interpretation, I would I would what do you say? I would warn you to deviate from this physical picture. You should not deviate from. And there is no other picture. At least on a fundamental level, something of this sort is only going to happen.
okay, okay, okay.
Okay.
It's
Maybe
okay
the,
now.
the way you are maybe the way you are presenting it, especially for your problem, it might be applicable, relevant, and you can go ahead with it. But in a general sense, if you're deviating from this picture, you might be going in the wrong directions. At least this is as far as I can tell you, because I am also not sure of what problem you're mentioning. Okay, that is one thing. But I will go ahead and tell you one more thing, that eigenvalues are also associated with the stability of a system.
Yeah,
Okay. So that is also something that we need to look at. Eigenvalues, if are positive, uh, at least the real part of eigenvalues are positive, that means that that system will explode. See, if you think, let's say, just assume that you are evolving in steps. In the first step, you take a vector and you operate it, you use this tensor to operate it, and this is your vector for the next step, and you keep doing it, a multiple rounds of operation by this tensor. If your eigenvector is positive, if you're scaling in the direction of eigenvector, if you're increasing the length, what you will observe is in several steps, this length of the vector will keep on increasing, right? Because the eigenvalue is positive. So essentially the value is going to infinity. But if your eigenvalue is negative, you're going to zero. It will keep on decreasing. Yeah, it has to be negative, right? If it's not negative, lambda has to be
and
it has to be small, lesser than 1. Then
yeah,
it will continuously shrink. But lesser than 1 is associated with a negative lambda.
can I say something? Just
Yeah, yeah, yeah. Go ahead.
you have one better thing with there. You will we define parabolic, elliptical, and hyperbolic equation based on eigenvalues, the negative positive thing.
We do that.
There
Do
can be
we do
related.
that? Let me think. Let me think. You're kind of right. In PDEs, I think you're kind of right. Let me check. Uh, Partial differential equation. Let me check that. You're kind of right. I think in PDEs, there. Let me check. Classification. Uh, yeah, parabolic. Eigenvalues are all positive or all negative. Eigenvalues are all positive except one that is zero, and there is only one negative eigenvalue. Yeah, that can also be true. Now let's look at what eigenvalue is this. In this equation, what is the eigenvalue? You're kind of right, I guess. Eigen, let me go up. See, here they have mentioned eigenvalues, right? But what is the tensor that we're talking about here? It is also important.
Actually, so that is the coefficients of the
This.
derivative 5x,
Hmm.
5x, 5y, those things are there, right? So the tensor formed is from the coefficients. The
Yeah, this
PDE,
B and C, right?
yes, yes, A, B, C, those things.
Yes. So now B square minus AC is, but my question is, so the classification depends on the signature of the eigenvalues of the coefficient matrix. See, eigenvalues are always associated with matrix. What is coefficient matrix? A, the eigenvalues of A it says, right? Not C though, huh? What is AIG? AIG. Wait,
AIG,
this is.
ABCs are all AIGs, sir.
Is it?
Yes, yes, sir. Because the general form of the PDE, it is written as sigmas, right? If you go down, I can show you. Yes, sir, right there. Just
Tell me, tell me.
see, it is written sigma y equal to 1 to n a y. I cannot read it.
Yeah,
It's in
yeah,
small.
fine.
It's
I'm
very small.
following.
So if you take expand the summation, it will be of the form of a phi xx plus b phi xy plus c phi y that way. So this aij thing, those are the coefficients a, b, c, and all. So we will get a
Right,
matrix. We'll get a matrix.
right, correct, correct. I got your point, got your point. So basically, see here also, it is kind of a vector. This is also a vector. This partial derivative, this A is definitely, where did it go? This one only. Just like how you mentioned, this is Aij.
Yes, yes. If
Now,
you
let's. Hmm. So, but
if you
just
expand
want.
the
Hmm.
summation, that will be of the form of a dou square u by dou x square plus b dou square u by dou x dou y that way.
Correct, correct. And again, here we will note that this is also getting into a form of matrix multiplication multiplied by a matrix multiplied by what? A vector, isn't it? Like Aij will be the elements of coefficient matrix, right?
Yeah,
Again, these are
aij
the
will
coefficient
be a
matrix.
square matrix.
Wait. Aij is itself a coefficient matrix. Wait. So Aij is a matrix in itself. That is
Uh,
also important. Hmm. Shivang was saying something, it seems.
yeah, actually the thing is like for any equation with higher order coefficients, those lower order terms are neglected in while we need to classify. We only take there's higher order terms where we write it. That's what there in this summation form is written. Only higher order terms which have del square u upon del x square or del square y upon del y square. And the second thing is the mix del square u upon del x del y. Such kind of things. Only those coefficients are considered. And there we
Yeah,
define B, A, and C associated with x. Those coefficients are a, b is this mixed up, and c one is the this thing, and from that we make this equation b square minus 4ac. Actually, yeah,
yeah.
here,
This is what you're saying. Got it. Yes.
yeah, this is what I am saying. Yeah, the uxx, uxy, and uyy. So from there we
Now,
make this
if
equation. We can write it in that form also, like a minus lambda equals to c. That form also can be written. From that this thing comes b square minus 4ac is less than 0. My concern is like here we are saying eigenvalues are positive, all positive or all negative.
hmm,
So does it make sense, like, because the question is actually a little more far. I will come to that next thing. The eigenvalues are all positive or all negative, it means it can only expand in either direction. Like if we just assume it to be in a direction sense just for physical significance, maybe it has some different meaning, but all in one direction or next direction. Why I am asking is
hmm,
because based on elliptic equation we have characteristic curves. and those characteristic curve will define the behavior of fluid, that in what direction that information will travel. So there I am going actually one step by step, but once the one thing I want to understand is this: it does what I'm saying is right, means that if all eigenvalues are positive and negative, then it means that the vector with what is representing eigenvector, that can only be expanded or like compressed in particular direction. Can I say that?
Yeah, you can say that, but you have to do it. You have to be careful about it. So
Yeah,
when
yeah,
you're
I
saying it
understood your
is,
point. Yeah, that completely I understood that it is not physically correct, but just for sake of understanding, can I
it
say?
might be. My only point is it might be. We have to be sure about it. When we say this eigenvalues, we will have to see what is this matrix trying to do. What is your output matrix? What is your output vector, input vector? When you
Okay.
say that input, if you can correlate a physical meaning that in this direction, in the so that when you say direction, you will have to see the direction. So vector, you will have a vector, right? Input vector. Then eigenvalues will correspond in the direction of that input vector. You will
Okay.
notice that along the eigenvector direction in the sense of input vector, output vector is also parallel to it.
But
So in that
actually,
sense, you have to see that what does direction mean? Is it a physical direction or is it a direction in a phase space? So there the term comes phase space. So if suppose now my only point here is just one last thing, and then we'll try to close. I'll take more questions next time. Actually, I have to travel to Hyderabad today. Anyways, suppose there is this function of there is some function called f of x comma y. X and y are physical space. Let me take it as u, some vector which is a function of u, which is a function of space. Suppose there is another function which I say this thing. Now the eigenvectors of A are actually not in a physical space, but in the space of U. That is important. So it's not a physical space. Sorry, it's not a physical space, but a phase space in the space of U, not physical space. Only there you have to be sure. So we will have to see what are these eigenvalues in the sense of. I cannot recall it right now. Maybe I'll see next time if I can. So yeah, in this equation you have, we can see if one eigenvalue is zero. It says, right. So we can see that what is going on in what is that eigenvalue representing. We'll have to look into it in detail because it is not
yeah,
always physical space. That is what I'm trying to just point out.
just
In this case, it will not be a physical space. Yeah,
can I say? Okay. So the thing is like if you can search about characteristic curves for elliptical equation,
I know about
and
them. I know about
yeah,
them.
no, no,
But
just
that
open
is
so that I can explain you the question. I'm requesting in some tab.
okay. 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 Characteristic curves.
Yeah, PD. Yeah.
Hmm.
For
Yes.
elliptic equation or like hyperbolic equation, hyperbolic equation.
They don't exist in elliptic. They exist in hyperbolic.
Yeah, that's what I'm
Yeah.
saying. Hyperbolic.
But you can go ahead and tell me the question while I open it.
Yeah, because in that curve we have that characteristic line, and
That
that
line is not associated with eigenvectors.
oh, that's what I am conclusion I am making because it is quite
Why are you? I told you, right? See, this is why I gave you an example. Just because I am saying a direction, it does not mean a direction in the physical space. Why will I? See, with this example, you need to understand when I say eigenvectors, it will be an eigenvector not in physical space. Look at this equation. It will be a vector in the U space. It will not be a vector in the physical space. Why will the characteristic curve be the eigenvector there? What is your physical? You have to be mathematical, right? You can't just say because I have a vector here, I have a vector here, I will associate them and I'll say this vector is associated with this vector. Does not work like that. You have to do it properly. See if that eigenvector is actually associated with the characteristic curve.
okay.
So
So
in your hyperbolic kind of situation, there is a situation in hyperbolic equations. There are lines along which uh, uh, the
gradient
derivatives
normalization.
are uncontinuous.
Yeah.
right? So there you have to see if that actually correlates with the eigenvectors or not. We'll have to actually see. But I think it is not related with that. It is related to what? It is
Can,
related with your um it
just a
is
minute. Can I say something?
no, wait. Don't say something. Wait. So the slope of eigenvectors, method of characteristic lines. Let's look at that. So in characteristic lines, actually the slope is defined by some manner, and it is not the eigenvector as far as I remember. Let me see. Characteristic lines. Yeah, so it actually in your hyperbolic situation, it actually depends on your local velocity and properties. This is the characteristic line. It depends on theta and mu, which is like it depends on local velocity. It keeps on. So in a hyperbolic situation, a characteristic line might curve. It is a curve, which will not make sense for you if you associate a vector with the problem, because vector has a constant direction in space. But in a general PD hyperbolic problem, characteristic curve might be a curve. It does not have a unique direction. So it's not always that every direction is associated with an eigenvector or eigenvalue of that sort. So you have to be more formal about it. Yeah, go ahead, Shivang now.
Yeah, actually, the thing is like you have made a point because these are curved, not lines. So I cannot this has cleared my confusion. But why I am confused is because like why I have drawn that conclusion because because when we find the eigenvector, the equation give us correct characteristic curve. That's why I am making that conclusion. But they are not actually going to come like
Confusing. Can you tell me how when you're trying to you tell me how when you're trying to derive an eigenvector, where do you get a characteristic equation? You tell me.
this
That
thing that
characteristic
these.
equation is different. You're confusing with different terminologies. You're mixing up. I think you're talking about the characteristic equation of the matrix. Are you talking about this? I don't know if you're talking about this or not.
No,
Not
that b
sure.
square minus
Probably.
4ac, actually that b square minus 4ac will give us characteristics line.
See,
Is that
my only suggestion, I have to actually stop now. I can't continue because it's
Okay.
yeah. Maybe I'll do it later on. There is another I2 or something. There is this is also called characteristic equation, by the way. And then you have plus determinant A equals to, this is also a characteristic equation. To be if you hear about, if you learn about Cayley-Hamilton theorem, you will come across this equation. Okay, then I2
Yeah,
is
yeah.
also some, right? My
Yeah,
only point here is that please look at the problem again. Try to see if the two things are actually corollary. Then maybe you can draw a physical explanation. But in general, it is not just like it won't make sense. Okay,
yeah, I understand. You
I
made
don't
the
know.
point. Actually, it's clear. It's almost clear.
Yeah,
I can go by the thought process. Then
yeah, you
I
can go
think
ahead
I
and
will.
see if there is an eigenvector kind of situation happening, then you are right. But generally, I think it's not the case. But anyways, I will not ponder, because again, method of characteristic is something, or characteristic equation is something not that I'm not working on currently. So yeah, you can explore that. Yeah,
Yeah. Thank you very much. Thank you.
yeah. Thank you, guys. So Apur, you have any questions? We'll continue the shooting method next time.
okay, so no sure. I'll
Sorry.
also rewatch the lecture again. Maybe that will be better for me.
Yeah. Okay. Right. Okay, guys. Bye.
Okay, so bye.
So see, just one last line. The slopes of the characteristic curves are actually dependent on, see, the local velocity and the local speed of sound. If the local wave velocity, so wave velocity and the local velocity, particle velocity. So that is what defines the slope of a characteristic curve. I don't think it is related to some eigenvectors or anything. I'm not sure. Maybe it is somehow related, probably, but generally I don't know. I don't see a direct relation there. Anyways,
I
okay.
think he has taken that from Suman Chakravarti's lectures on CFD because he is the only one who discussed like use of eigenvalues in PD classification, the one which you showed on Wikipedia.
Actually,
Maybe.
this is the curve I am looking for from the very starting. Actually, this equation dx upon dt is equals to u minus c. Is this equation will come when we solve the characteristic equation?
I don't think so. That is what that I don't think so.
Okay.
I don't think
Okay.
so. This is coming from, I'll tell you what this is coming from. See,
Yeah.
eigenvectors are not, see that the explanation I tried to give you is actually an important clue there. You need to note when eigenvectors and eigenvalues are talked about, you need to see what is this vector in which space, which vector space. It can be a phase space. I'm not sure if I'm pretty sure that you won't be aware of phase space or anything. But see, this is not the physical this is not a physical vector u. Velocity field is not a physical space. It is not the Euclidean space. You understand? Velocity is not physical space. You understand, right? X comma y is a physical space, but u does not exist in this space. It
Yeah,
has
I
a vector
understand.
space of its own. So the eigenvectors will lie in that space. It cannot lie in physical space. So they actually, this equation actually comes by combination of uh, again conservation of mass and conservation of momentum, and then you put what do you put there, Prandtl-Meyer equations and so on. That is where it comes. This thing comes. You have to do a lot of PDs. This thing this is method of characters. I hope. So that comes from there, but I don't
Actually,
see any eigenvalues. Or, hmm.
that equation
Maybe you
what
can
we have
come
seen
more.
in
You can.
Wikipedia,
Hmm.
it actually derived here. The final result will be this.
I maybe what you can do is write it up. Show me how it comes. It would be nice to see that. Okay,
Yeah.
that would be nice to discuss. Yeah, you can do it and show that if it follows. If you can actually show. See, because here the reference of U and C will come, but there is no reference of U and C there in our Wikipedia page. So not sure, but probably let's see. Let's see, because
It's fine.
there,
You have
as you said,
already, yeah, the intuition is clear. You make the point. I understood your point, and based on it, I think I can draw the conclusion that how it is coming. That's
great.
really nice. Thank you. Thank you very much.
Thank you. Thank you, guys.